So in chapter number 5, as I mentioned, we will be covering 3 different type of circuits. We will be covering integrator circuits that calculates area under curve. We will be covering, of course, differentiator circuit that take the slope of your input, and that is your output, the slope of the input. And of course, we will be covering phase shift circuit such that your input and output phase of waveforms is going to be different, and you can set how much difference do you want between the input and output phase. So these are 3 classes of circuit that we will be covering. Under these classes, we have different circuits. Start with the true integrator circuit. So integrator and differentiator circuit, also called wave shaping circuits. Why do we call them wave shaping circuits? Because let's say if you have a differentiator circuit and you have a constant DC voltage, and you want to differentiate that constant DC voltage, what you're going to get? A DC value or a constant value. When you differentiate, you're going to get what? 0. You're going to get 0. Likewise, if you have a slope and you differentiate a slope, AX, AT, what you're going to get? A constant value, right? Differentiate AT with respect to T, you're going to get a constant value. So it changes the shape of your input signal with respect to the output signal. You give a slope, a linear line basically, and then you get a constant value at the output. You give, so if you give a triangular signal at the input, for example, if you have a triangular signal like this, sawtooth or a triangle signal, is that if this is the input and you are taking the differentiation of that signal, then each line is going to give you what? This is a slope, a straight line is going to give you a constant value, right? DC value, because this is AT, this is negative BT, the slope is negative, slope is positive, going up, going down. So that's going to give you a positive value, that's going to give you a negative value. So you're going to get what? You're going to get a square wave, something like that. So it changes the shape of the signal. Differentiators, the same thing with the integrator circuit. With the integrated circuit, if you have your square wave or a constant value, then integration of A is going to be what? With respect to T, let's say, AT, right? That means A is going to be converted into a line with a slope A. So it changes, it's the opposite of differentiator. Of course, integration and differentiation, they're the opposite operation. So if you give this signal at the input of an integrator, you're going to get this at the output of the integrator. So again, it changes the shape of the signal. And that's what you see, it is also called wave shaping circuits. As the output signal shape can be changed based on the input signal. For example, if input is square wave, constant high or low, output of an integrator will be a triangular signal, as we just discussed. Now, this is a true integrator circuit, and then we're going to look at the AC integrator circuits, the practical integrator circuit. Now, in this true integrated circuit, you have the input, you have the resistor, and in the feedback loop, instead of a feedback resistor, we have a feedback capacitor, as you can see. Now, you do the same thing when you're doing the derivation. You have the virtual ground over here at the inverting input, and your current is, it's written as small, so let's say I input T is your current here, and then I feedback T or whatever it's written here, ICT, let's say ICT is the current in the feedback loop. So you apply KCL at the virtual ground, and these two currents are equal. I input is equal to IC. What will be the equation for I input in terms of Ohm's law? Who's going to tell me? This is V input. Yes. Yeah, so we input T over R, we input minus 0, and then the capacitor current. What will be the expression for the capacitor current? No, we are not going into the phasor domain right now, in the time domain. Come on, guys, there are so many students, why only 2 people are answering? What is the relationship between integrator current and the voltage? Relationship between integrator current and voltage. What is the expression? How do you relate them? Integrator current and the voltage, or not integrator, capacitor current and the voltage. Okay. Well, we're not going in the phasor domain, in the time domain. Yes, then you said that IC is equal to C dV over dt. What's going on, guys? Come on. C dV, now voltage across a capacitor, I can write down dV CT, which is the voltage across the capacitor over dt. Now voltage across the capacitor VCT is virtual ground minus the output. C d over dt of negative V out. Which means I have d over dt of V out t is equal to negative V input t over RC. And if you take remove the differentiation, then you're going to go ahead and integrate both sides with respect to t. Then this is going to be removed, V out t, and if you want to show it from, let's say, from initial capacitor value, initial value V out at 0 and V out at t dt. Or dV naught, sorry, dV naught integral negative at t is equal to 0 to t 1 over RC V input t dt. So you are going to get what? Output t minus output at the initial value 0 is equal to negative 1 over RC integral of 0 to t V input d. And that shows you, and if the initial voltage at the output is 0, then simply at output t, it is going to be negative 1 over RC, the integral of the input voltage between 0 and time t dt. If this is 0, if this is not 0, if there is a voltage at the output at the beginning time, whatever beginning time you're using, the reference time t is equal to 0, whatever reference that you're using, if there is a voltage at that time at the output, then you do have to consider that voltage right over here, V out at 0. But if that voltage is 0, then it's simply going to be V out t is equal to negative 1 over RC integral of input voltage times dt. So this circuit is doing what? This circuit is taking the input, integrating the input from 0 to time t, and of course this you can assume to be the gain 1 over RC, and basically projecting that quantity at the output. This negative sign represents what? The phase difference or if you have, let's say, if you have the square wave like this, then for when the input is high, the slope is going to be negative. So it's going to go negative because of that negative sign. And if the input is low, the slope is going to be positive because of that negative sign. That's how you are going to interpret that. If it's a sinusoidal signal, then simply you're going to add 90 degrees between the input and the output, basically. If the input is sinusoid, then when you integrate a sine signal, you get a cosine signal. When you integrate a cosine signal, you get a sine signal in general. So it's a 90-degree phase difference. So if I do ask you to do derivation, I don't really usually ask to do derivation of integrator differentiator. It's more like a problem and give an input. As we're going to do the examples, input signal is given, then you have to figure out what will be the output signal and all those things. So generally, I don't ask you to do the derivation, but I do ask you, if I do ask you, show the relationship between the input and the output for this, then this is a derivation right in front of you. And this is how you're going to show that applying KCL at the virtual ground, which is here, show virtual ground is here, then input current is equal to the capacitor current. Write down the equation, and then that is going to be the relationship between the input and the output. So this is the derivation for this circuit right there in front of you. The same derivation shown here. Okay. One problem in the true integrator circuits. That's why we don't really use true integrator circuit actually. And the problem is any small noise or DC biasing voltage that may appear at the input can produce a ramp output, which over time can keep on increasing until the output voltage hit saturation. What is that supposed to mean? So remember, DC voltage turns into a ramp voltage if it is passed through integrator, right? If you have any small noise signal at your input, the negative input, the inverting input, right? Right now you have a signal connected. You have your input signal connected at the inverting input. But in addition to the input signal, or even if you don't have any input signal, let's say if input signal is 0, but somehow you have a stray noise, or you have DC biasing current because of the biasing of operational amplifier, you have DC biasing current that is going constantly inside your inverting input. No matter how small quantity that is, but since that's a DC value, it may be in microvolt, it may be in nanovolt or whatever. But if you just leave that circuit on, what's going to happen? Over time, it's going to start increasing and start becoming a ramp because your input is a stray noise voltage or the leakage current from the biasing sources or whatnot. And if it will keep on increasing without having any input at present at the input, then eventually it's going to hit the saturation voltage, 15 volt, negative 15, whatever, and then it's going to saturate. The output is going to saturate at that time. So that is a potential problem that is possible. I'm not saying it will always happen, but it's possible. And to take care of that problem, we kind of modify this circuit a little bit. So this is the problem. Due to this potential issue, we modify the circuit, and our modified circuit is called AC integrator circuit. And it's going to come after we discuss the true differentiator. So true integrator circuit, basically you have the input, you integrate the input, and that is your output. Of course, there is a gain associated with that as well, which is 1 over RC. This is lab number 4, by the way, that you will be doing next week. So make sure you understand it, because again, when I ask you to explain, if your input is this, output is that and stuff, you will have to explain it to me as why you are looking at that output, why is the output of this circuit. True differentiator circuit. It takes the differentiation of the input and produce at the output. That's the true differentiator circuit. We switch the location for the capacitor and the resistor. So now capacitor is in the path of the virtual ground and the input, and resistor is in the feedback loop. And once again, when you apply KCL at virtual ground, input current, the capacitor current is equal to your feedback current. So capacitor current is equal to the feedback current, or the current passing through the resistor R. And that gives you capacitor current is this, C dV over dt, C times V input minus 0, so it's V input over dt, and the resistor current is this, 0 minus V out 2 over R, so minus V out over R, which gives us negative RC dV input over dt. So V out is equal to negative RC dV input over dt, derivative of the input times RC, and of course the negative sign is there. There's a problem again with the true differentiator, and the problem is again the noise problem. If you have any small noise spike at the input, it can lead to a very large output spike. Why? Because remember, what is differentiator? dV input over dt, right? It's the rate of change. It's not the actual value of the voltage, it's how fast the input is changing. That's what it is projecting at the output, rate of change of the input, right? So even if the input is a small noise, but if it lasts for a very small amount of time, the rate of change can be very high. So if you have 1 microvolt at input, let's say a noise, but it lasts for 1 nanosecond, then your rate of change is 1000, right? 1 micro over 1 nano, rate of change is 1000. And that 1000, of course, is going to be projected at the output in terms of a spike. So it's going to have a spike. Of course, the spike cannot go forever. It's going to go up to whatever the saturation limit is, but it's going to have a spike from 0 to 15 volt, let's say, saturation limit. And that is quite possible because your noise voltage is always very small and it can last for a very small amount of time. And that's why we don't use this true differentiator, because of those spikes that are very possible at the output. And that's why again we modify the circuit and we create a circuit which is the AC the differentiator, or differentiator bandwidth. I believe, I don't know, in the lab, I think we are still using true differentiator and true integrator. Let me check real quick. Lab. Experiment 4. Yeah, so this is we are using the low frequency differentiator, which is, and the AC integrator. So we are using the modified circuit. We are not using the true integrator and true differentiator, but the AC integrator and low frequency differentiator. Okay. What are your inputs and what you are expecting at the output for integrator and differentiator? So if you have a constant DC, integrator is going to give you a ramp. Constant DC, integrator is going to give you a ramp. And differentiator is going to give you a 0, as we discussed, because you're integrating the input and differentiating the input. If you have a square waveform, integrator is going to give you an up and down ramp, of course. So this is a square waveform. You're going to have a ramp signal going up. You have a ramp signal going down. So a triangular waveform, basically, output of the integrator. And the differentiator is just going to produce impulses whenever you have these changes. Because again, the changes are happening in a brief amount of time, right? So when you are doing the, and let's say your square wave, of course, all the practical square waves, they cannot go instantaneously from 0 to 1 or 1 to 0. For practice, it is impossible. because it will always take some time for any equipment to go from a high level to low level. Very small amount of time, but nevertheless, there is a time that is going to take, which we call rise time, as we discussed, right? In the last chapter, we discussed rise time. So your square wave is not really square in this sense, but it is a square in this sense, that you still have a slight slope when it is going up, which is called the rise time, and when it is going down, which is called the fall time. Of course, when you take the differentiation at either the low level or the high level, that differentiation is going to be 0 because it's a constant value. But when it is going from high to low or low to high based upon how small of a time is that, then of course, when you take the differentiation of that rate of change, then you will get some value. Right? If it is going from 1 to 0 and if the time is 1 microsecond, then when you take dv over dt, you're going to get a spike at that time. So you're going to get impulses. We discuss impulse, of course, in integrated circuits and power system and in other courses. So you're going to get impulses whenever it is going from high to low and low to high. So if this is passed through a differentiator, then you're going to get this basically 0 impulse, something like that. So 0 and then impulse, 0 impulse. Anytime you have the transition, you're going to get impulse. If your input is a triangular waveform, then integrator is going to give you parabolic waveform. Integration of AT is going to be A by 2t square. And your differentiator is going to give you a square waveform. Of course, triangular, when you differentiate that, it's going to be a constant value when it is going up and a constant value when it is going down. So positive and negative values. If you have a sinusoidal input, then of course, both integrator and differentiator, they're going to give you sinusoidal voltages, although the phase difference is going to be there. Cosine becomes sine, sine becomes cosine. So some of these you are applying next week as your input for integrator and differentiator. So make sure that you are expecting those waveform. And what is the peak value of the waveform? We're going to discuss that, how you calculate the peak values of the output waveform and all those things. So once again, when you're doing the pre-lab, make sure you understand it properly, how you're calculating the peak value, what should be the shape of the waveform, because you're going to observe that, and I'm going to ask you questions about that as well. Okay, let's look at example 5.1, a true integrator circuit. So you have negative, positive, or this is your circuit, true integrator circuit. This is your input, and this is your output. R is 1 kilo ohm, and capacitor is 1 microfarad. And this is the input to the integrator. So I'm just going to move it here. This is what is given as the input. Determine the output of the circuit. So determine means you have to, of course, you already know what the output shape is going to be. Who's going to tell me what is going to be the output shape of this circuit? Not the value we're going to calculate, but what will be the output shape of the circuit? Triangular waveform, exactly. Because input is a square wave. It's going to be integrated, and output is going to be a ramp function going up and down, which will make it a triangular waveform. So the output is going to be a triangular waveform. We already know shape of the output. So that's the first thing. The second thing is, what will be the values of those triangular waveform? What will be the peak values? What is going to be this? What is going to be this? If it is centered around a DC value, what is going to be that DC value? So all those things we have to determine basically. It's important to observe the values here. So I'm going to write down what I gave you because this is very small. This is 5 volt. Of course, this is 0. And this is negative 5 volt. input. So this is a square wave between 5 and -5, and your time period is 1 millisecond for this wave. Okay. Now, when you are, of course, when you know, you have the formula for sure that you can use to calculate that. V out is equal to V out t minus V out naught, -1 over RC V input dt. But if a shape is given to you like this, a square signal is given to you, remember integrator is going to basically, you have to check what is the area under curve, right? And you have to add that area under curve, and that is going to be the output multiplied by 1 over RC. So it's easy to calculate the output. Instead of going to the formula and do the physical integration, you can do that for sure. But if you know what is the shape of the input, and if it's a periodic signal, then you can always calculate area under curve easily and determine what will be, because we already know shape of the output is a triangular waveform. All you need to know is what is the voltages, the peak voltage and the negative peak voltage of that triangular waveform. Thus, you want to determine. Shape you already know. And of course, the time period is also not going to change. The output triangular waveform is still going to be 1 millisecond long. So the period is going to be the same. How are you going to calculate the peak? So you have, of course, let's write down formula first, but we're going to just use the area under curve instead of using formula. So the formula, of course, or the equation to calculate so this is the equation that we derived earlier to calculate. Let's calculate what will be the peak to peak output voltage. To calculate the peak to peak output voltage, either we can use the positive area or we can use the negative area. You can use one of the areas, either positive area or negative area. And the peak to peak output voltage, of course, the gain is 1 over RC. Positive or negative area. Don't use the negative sign, but just the area. That's going to be the peak to peak the output voltage. The gain of the amplifier, amplifier is 1 over RC, and you calculate the positive or negative area, whatever, because the area is the same. So this is V out peak to peak. 1 over RC. R is 1 kilo ohm and C is 1 microfarad. So 1K, 1 micro is 1 milli. So 1 over 1 exponent -3. 5 volt times 5 volt is the height and times half millisecond. So 5 times half millisecond. .5. That's the peak to peak output, 2.5. So the output waveform that we already know, it is going to be a triangular waveform. And remember this negative sign. That means when you have the positive output, your slope of the output is negative. And when you have the negative output, your slope of the output is going to be positive because of this negative sign. The peak to peak value is 2.5. So if I have 0.5 millisecond, 1 millisecond, 1.5 to, let's say this t is in millisecond. .25, and yes, yeah, because of this negative 1 over RC. Remember, it's negative 1 over RC integration of V input t. So because of this negative sign, if your input has the positive value, then your output is going to be going down. Like in this case, of course, we know output is a triangular waveform. So if input is positive, output is going to go down because of this negative instead of going up. So the slope is going to be negative for the output. And when the input is negative value, the slope is going to be positive for the output. That's what that negative sign is doing over here. So initially we have the positive value, 5 volt. So the slope at the output is going to be going down from 1.25 to negative 1.25 because peak to peak value is 2.5. And then it's going to be going up from 0.5 to 1. And then again, it's going to be going down. And then going up. And then this cycle, of course, will keep on going. What is that? Yeah. Because if you look at the input, in one cycle, you have the peak to peak value. Like you're going from 0 to 1 millisecond, and you have 0 to half millisecond, it's peak to peak value. 0 to 0.5 millisecond, it is going from 5 volt to negative 5 volt. Observe, 5 volt to negative. So in half of the period, you have one peak to the other peak, and then in the next half of the period, from the negative peak to positive peak. So when you're calculating the area under curve, then in half of the cycle, the output is also going to go from the top peak to the bottom peak, and then from the bottom peak to the top peak, making it one complete cycle. So that's why each area is going to give you peak to peak value from the positive area as well as the negative area, not just the peak value. It's going to give you peak to peak value. You already know the shape of the output. That's the thing. You already know shape of the output is going to a triangular waveform. All you're trying to figure out is what are my limits, right? So in half of the cycle, it is going from one peak to the other peak, and rest of the cycle is going from, because you have to complete one cycle. This is one cycle. The V is here. V is one cycle. This is one cycle. So from top peak to the bottom peak, and from bottom peak to the top. And even if you apply the formula, 0 to t by 2, and then t by 2 to time period, you're going to get the same result, basically. You can apply the formula, you're going to get the same result, exactly the same result. If the input is this triangular, then what we are expecting at the output? Not sinusoidal. Parabolic waveform. So the output is going to be a parabolic waveform. If this is the input, then it's going to be parabolic waveform. And first, it is going to increase because the slope is going down. So in half of the cycle, it is going to increase, and in rest of the cycle it is going to decrease because the slope is going up. So the peak to peak value is going to be from this point to this point.